Hi, everybody. Good evening. Welcome to our meeting today. We have our guest speaker here, and we're very happy to, please give a round of applause to Perry Edmondson. So Perry is here to speak about a very interesting topic, and when he told me what he's going to speak about, Canada's Lunar Rover mission, I'm like, please come to our meeting. So Perry has been a lifelong enthusiast and avid supporter of manned and robotic space exploration. He has over 28 years of experience in the Canadian space industry, working on commercial and government space projects in various technical and management roles. He's obtained a couple of degrees in engineering, including from University of Ottawa, and a master's degree from University of Southern California in LA. He's a licensed professional engineer. For the past 7 years, as program manager at Canasys, he has been managing numerous space mission proposals, concept studies, and technology development projects for the Canadian Space Agency, primarily related to lunar rovers. He is currently managing the development of the CSA's Lunar Rover mission at Canasys. So welcome, Perry. Over to you.
Thank you very much. Well, thank you for having me this evening. And I'll just say hello to our participants online as well. I will probably wander away from this podium a bit. So unfortunately, that means online. You may not be able to see me, but it's more important that you see the presentation anyway, and you can listen along. So yeah, so I'm very happy to be here. My name is Perry Edmondson. I'm a project manager at Canadensis Aerospace. We are a Canadian space company headquartered in Bolton, Ontario, just north of Brampton. We have a second facility in southwestern Ontario in the play town of Stratford, best known for live theater. But yeah, we have a facility there as well. That's actually where I spend most of my time, because I live in Waterloo, Ontario, so a little bit closer to Stratford than to Bolton, but I do manage to get to Bolton once a week or so as well. And most of our team that's working on the Lunar Rover mission is actually in our Bolton facility. That's where most of our employees are located. So I'm going to talk to you tonight about Canada's Lunar Rover mission. And I always like to start off when I'm speaking to groups like this by asking, how many people actually knew Canada was building a lunar rover? Okay, all right. Actually, that's more than I get in a lot of talks that I've done. So that's good. You guys have been doing your homework. Canada is in fact developing a lunar rover that will be going to the moon. And I'll be telling you a little bit more about that and about kind of Canada's role in general in lunar exploration. And yeah, so let's dive right in here. And if with any luck, this remote will allow me to switch. Click the mouse. Okay.
It was working until Rob.
It was working. I can vouch for that. Okay. All right. So, in case you didn't know, Canada is going to the moon. We are one of many countries that are participating in this international endeavor of returning to the moon after many decades of absence. The first time around, of course, it was heavily dominated by the United States. There was at least one other country that made an attempt to do that. The Soviet Union at the time as well had limited success, never sent any crewed missions to the lunar surface. Only the Americans did that. And then after that race was won, they turned their attention to other things, came back closer to Earth, decided to develop the space shuttle and the International Space Station, and have spent the last several decades in Earth orbit. And it's only, in the last 10, 15 years or so that there's been this interest to expand further out again into cislunar space and get back to the moon. So Canada is a participant in this endeavor. There was a commitment made by the Canadian government a number of years ago to develop another Canadarm for a space station that's going to be in orbit around the moon called Lunar Gateway. It will be a smaller space station than the International Space Station. And it will only be crewed periodically. It will not have continuous human presence like the International Space Station does. It will be specifically just for sending sorties down to the lunar surface and back. So it's kind of a bus stop along the way from Earth to get to the moon. And so Canada has committed to supply the Canadarm3 for Lunar Gateway to help build and maintain the station and dock visiting crewed vehicles when they arrive. And in exchange, we get to send some astronauts. So first up is Canadian astronaut Jeremy Hansen, who will be flying on the next crewed mission of NASA's Artemis program, which is the Artemis II mission. It will be the first time a crew has flown on the new space launch system, the Orion crew capsule and the SLS rocket. That is now scheduled to fly sometime next year, 2026. I think officially they're still saying around this time next year that mission will fly. And that crew, Artemis II, will not actually land on the lunar surface. They will take an outbound trip past the moon and kind of slingshot back around it and come back past the moon again and come back to Earth. So they won't even technically orbit the moon. They'll do kind of just a flyby outbound and back. And it's really just a test of the SLS to make sure it's capable of flying future crewed missions. There will be missions that do take crew to the surface of the moon after that over the next number of years. Maybe Canada will have another astronaut that someday actually gets to set foot on the moon, but there's nothing definitive planned for another Canadian astronaut to the moon at this point, but fingers crossed. Another commitment that the government of Canada made in addition to Canadarm3 is a program called the Lunar Exploration Accelerator Program, conveniently called LEAP. Got to wonder sometimes who comes up with these names, but so what this is a commitment to develop scientific instruments for lunar exploration, and the flagship program is the Lunar Rover mission. And so that's what I'm going to talk a little bit more about tonight. So what is the Lunar Rover mission? Canada has planned to send a 42-ish kilogram. That number has kind of changed a little bit over the last few years, but started out at 30 kilograms, went up to 35. Now we're up to 42. And they've told us, no more. Can't gain any more weight. That's it. That's as much as you get. Anyway, so Canada will be sending this rover to the moon, packed with scientific instruments. It will be landing in the South Pole region of the moon. The South Pole region is a region that is known to contain a lot of frozen water ice. That has been detected through numerous missions orbiting the moon that has detected the presence of water ice at the poles. The South Pole is an area of great interest right now for future crewed missions. That is the region where they plan to land these future crewed missions, set up a habitat. And the plan is to take advantage of that water ice, harvest it for drinking water, breathable air, producing rocket fuel, all those kinds of things that need water. So rather than having to take it all with us from the Earth, which is a lot of weight to carry, a lot of water that they will need, which translates into a lot of cost. Plan is to actually use that water in situ from the lunar surface for what they need it for. So right now, the Lunar Rover mission, if you look up on the Canadian Space Agency's website, it will tell you that the launch is planned for no earlier than 2026. That is true. But I'm gonna tell you a little secret. Don't tell anybody I told you this. It's actually no earlier than 2028 now. There have been some delays in the program. This is an international collaboration between the Canadian Space Agency and NASA, the US. NASA has a program called Commercial Lunar Payload Services, or CLPS, which is a series of commercial unmanned robotic missions, precursor missions that they're sending to the moon before the crewed missions that start to go in a few years. The purpose of these missions is to explore the regions, various different regions of the moon, including the South Pole region, where the crewed missions are expected to go. Learn more about kind of what's there, the environment, so that they can better plan these crewed missions. These are commercially led missions. They're designed to be sort of lower cost missions that they can send, numerous of them to various regions of the moon and kind of spread out and learn as much as they can about the different regions of the moon. So we are going to be riding on one of these CLPS missions, along with several other payloads from US and other international partners. And if you've been keeping track of any of the recent missions that you may have heard about in the news, there have been a few of these CLPS missions that have flown already. Last year, in February, a company called Intuitive Machines flew their first mission to the moon. Unfortunately, when they landed, they did not stay upright. They landed, it kind of tipped over and landed on their side. This past February, just a couple of months back, they flew their second mission. And unfortunately, they had largely the same result on their second mission. It was the first mission to the South Pole region, and the South Pole region is more challenging to land a lander in for a number of reasons. I'll touch on some of those. And so, unfortunately, they were not successful in staying upright. They landed this time in a crater, so even worse luck than the first mission. And they also ended up on their side again. And so they were not able to get their solar panels into the sun to charge the batteries. And a mission that was supposed to last around 12 days or so ended up lasting less than 12 hours before the batteries ran flat. So that was unfortunate. There actually was a rover on that mission, which did not get a chance to deploy, which was quite unfortunate. So there has yet to be sort of a small-ish rover of kind of the size that we're talking about here for Canada's Lunar Rover mission. There has yet to be one that has been able to roam around in the South Pole region. So we expect somebody will accomplish this before we do, probably, but there'll be lots to learn still by the time we get there as well. So there you go. Watch the news for updates on the projected landing date, but you didn't hear it from me. All right, so let's talk a little bit about the moon itself. Why do we want to explore the moon? What's the big deal? So the moon, of course, as you all know, is Earth's closest neighbor. It's believed to have been formed in a collision between Earth and another large planetary-sized object in the very early days of our solar system's formation, about 4.5 billion years ago. And so it's widely believed that the moon is actually a piece of the Earth. And there have been, some samples from the moon brought back from the Apollo missions, as well as some of the robotic missions that have gone. And the study of the makeup of the material supports this theory that the moon is actually made from the same stuff as Earth. The moon orbits the Earth at a distance of about 384,400 kilometers away. The moon orbits the Earth once every 28 days, as we know. We see different phases of the moon that repeat on this kind of 28-day cycle, from new moon to waxing crescent to full moon to waning crescent back to new moon once every 28 days. And the moon also completes one full spin on its own axis in that same 28 days. And what that means is, from our vantage point on Earth, we are always looking at the same side of the moon. We never see the other side. It's always facing away from us. The side that faces us is always the same. So you might kind of wonder, well, that's kind of interesting. So do we know what the other side looks like? Well, we do. And that's because we've sent numerous spacecraft there to orbit the moon, to photograph the backside of the moon. And this is what it looks like. This image on the right-hand side of the slide here. You'll notice, if I go back to the previous image that I had of the near side, there are some differences. So the near side seems to have many more of these sort of smooth regions called seas, whereas the far side is much more full of craters. So kind of interesting. Sort of makes sense if you think about it. If there are objects coming towards the moon from other places in the solar system or outside the solar system, they have a better chance of hitting the side of the moon that's not sort of shielded by the Earth than they would hitting the near side. So that's probably why. Here's an image on the bottom left of this slide of an area of the far side of the moon called Zeeman crater. This was taken by a Russian spacecraft called Luna 25 back in August of 2023, just before it attempted to land on the moon and unfortunately was also unsuccessful. So you might think, well, how hard can this be to land on the moon? Like, didn't we do that back in the 60s? Well, as it turns out, it's still a hard thing to do. So countries and commercial companies like those in the US that are part of CLIPS are kind of having to relearn how to do this. And in particular, the South Pole region has some definite challenges that they did not experience back in the Apollo era when they sent missions. Most of those missions landed in the equatorial region of the moon on the near side, facing the Earth. And so things like lighting conditions were much more favorable, for example. They landed in full sunlight. When you're at the pole, if you've ever been to, let's say, the Arctic regions on Earth here, Arctic or Antarctic, you'll know that the sun for many parts of the year is very low on the horizon, casts very long shadows. So couple that with very rugged terrain, and you can imagine what the landscape looks like when you're trying to land there. It's very difficult to figure out what's a rock, what's a crater, what's a shadow. It's a pretty complex thing to do. So they're learning how to overcome some of those challenges. So what's life like on the moon? When we get there, what would we experience? Well, first of all, the Apollo crews found it is extremely dusty. So, and the dust on the moon is different than you might find here on Earth, where weather and water and other processes tend to kind of wear the sharp edges off of the dust and make it just sort of dust particles nice and smooth and round. On the moon, they're very jagged and sharp, and they cling to everything they come in contact with, and they find their way into moving parts or into folds in material of spacesuits. It's very abrasive and things get very quickly worn and damaged when they're exposed to this lunar dust. So extremely dusty, that's a significant problem to overcome. Very low gravity as well. So there is only 1/6 of the amount of gravity on the moon that we have on Earth. So great thing is, if you don't like what you weigh on Earth, take a trip to the moon. let's say you weighed 60 kilograms on Earth, you would only weigh 10 kilograms on the moon. If you've always wanted to do a slam dunk in basketball too, this would be another great opportunity to do that. You can jump really high. But it does make for sort of moving around and traversing on the moon a bit challenging. It's, the astronauts notoriously had problems with their balance as they were moving around. The Apollo astronauts, driving on the moon is a bit challenging because it's you're really sort of floating along, bumping along. And so, yeah, it requires extra care for sure. Temperature swings are crazy. So when the sun is up, it's up for 14 days straight. So the moon gets absolutely baked in sunlight, and especially at the equatorial regions where it's getting direct sun. And temperatures can be as hot as 110 degrees Celsius. So, and then conversely, when the moon is in the other half of its orbit and that part of the moon is in darkness, the temperature plummets and there's no atmosphere. So there's no modulation of temperature. It gets super cold, below minus 200 degrees Celsius. So managing this thermal environment is also a significant challenge. And you can imagine how challenging it would be to keep an astronaut alive in those temperature extremes. It's also very challenging to keep electronics alive, which normally require much narrower temperature ranges in order to survive and to function properly. So if the moon is such a harsh place to go, why would we bother going there? Well, it is our closest neighbor in the solar system, and there's lots we can learn by visiting the moon about the history of the solar system and Earth's place in it. We can practice how to live away from the Earth, a little bit further away than the International Space Station, which has been a great training ground as well. But comparatively, it's a lot safer than going much further away to somewhere like the moon or even further to Mars or other destinations in the solar system. So that helps us sort of take that next step and learn how to live away from Earth for extended periods of time. And eventually that will help us to learn how to do missions to places like Mars and elsewhere, which are much, much further away. And you can't just quickly jump in a ship and come home if something goes wrong. So I talked a little bit about the South Pole region of the moon. Just to revisit this a little bit. Here's a map that shows the South Pole region. So this is kind of a hemispherical map looking at the moon from below, from the South Pole. All those little blue dots that you see there are detections of water ice. So you'll notice many of them are concentrated inside large craters near the pole. But they've actually, in more recent missions, they've determined that there are signatures of water that are spread all over the moon. They're just more concentrated in these polar regions, and so they expect they will be easier to access and to harvest and use the water from these regions. So, like we said earlier, lots of uses for water, especially for human crews when they arrive there. And this is where they expect to be setting up a habitat for longer term exploration, human exploration. So here's a photo of the most recent Intuitive Machines mission that I mentioned that made an attempt to land in the South Pole region in February this year. Nice picture looking back at Earth there, but you can probably tell by the fact that a couple of the lunar lander legs are sticking up in the air that things didn't go quite as planned here. Yeah. So interestingly enough, in case you weren't aware, our company, Canadensis Aerospace, has developed a suite of camera products for space missions. And both the Intuitive Machines 1 and Intuitive Machines 2 missions carried a suite of Canadensis cameras on board. This image here that you're seeing was almost certainly taken with a Canadensis camera. And if you were following any of the sort of the progress of the mission as they were transiting from Earth orbit to the moon, they were kind of sending weekly updates with photos and things. Most of those images that they shared would have been captured by Canadensis cameras. So we're pretty proud of that. All right, so let's talk a little bit about what a rover is. So when we say rover in this context, we're not talking about this little guy on the top of the slide, although he's really cute. We're talking about something closer to the image on the bottom of the slide. It's a robotic vehicle, typically has wheels of some sort, roves around on the moon or on whatever planetary body it's being sent to. Typically is remotely controlled, might have some degree of autonomous capability to drive around on its own. And the best examples of these, or the best known examples of these in recent memory at least, are NASA's rovers that are exploring the surface of Mars, and have been for about the last 25 years, actually, since the original ones were sent there back in the 1970s, I guess. But anyway, so when we say rover, we mean it's either an uncrewed or crewed vehicle for off-road or off-planet exploration. It can carry a suite of scientific instruments to collect information. It allows up-close scientific investigations and measurements to be taken that you can't obtain from an orbit mission, for example. So as I mentioned, we know from orbit that there is the presence of water ice has been detected on the surface. What we don't know until we really get to the surface and take up close measurements is what form does that frozen water ice exist in? Is it large monolithic sheets of ice? I mean, could you put a pair of skates on and go skating on a rink on the surface? Probably not, but we don't really know for sure until we get there. It's more likely not at the surface, but slightly below the surface, maybe up to 1 meter or 2 in depth. And it's most likely distributed through the soil rather than in sort of monolithic chunks of ice. But we really don't know until we get there. So that's something that a rover mission allows us to do is get up close and take some measurements or even some samples. So that's what our mission and a number of other missions that are planned will be doing, taking up close scientific measurements to better understand what the surface of the moon is like, what it's made of, what resources might be there in terms of water and other minerals, and to ultimately learn more about that environment to inform plans for future crewed missions. All right, so I'll give you a little tour of our vehicle. Incidentally, this rover doesn't have a name yet. You might be aware that the Canadian Space Agency put out a naming vote on their website back in around Christmas time last year. They had collected a large number of candidate names from the Canadian space community. They had whittled it down to the final 4 candidate names, and then they had a vote. They posted a voting campaign on their website. So invited people to vote for their favorite names. They have not yet revealed what the chosen name is. So stay tuned. That last we heard, we should have known maybe this month, but this month's almost over. So not sure. And with the election happening, government kind of goes into a pause mode until the new government's in place. So sometimes that delays things. So anyway, we're still waiting to find out what the name is. For now, we call it LRM, short for Lunar Rover Mission. Pretty boring name, but that's kind of what we call it. All right, so I'll point out some of the rover's main features here for you. Size-wise, it's approximately 70 centimeters wide by 70 centimeters long by about 90 centimeters tall with the top antenna mast deployed there. You can see a kind of a pole sticking out the top of the rover with an antenna on top. That gets deployed once the rover's on the surface. And as I mentioned earlier, the rover weighs approximately 42 kilograms now, and we're pretty confident now that that's as much as it will weigh. It shouldn't get heavier than that at this point. There have been a lot of reasons why the mass has increased. We're trying to do an awful lot with this little guy, packing as much science and engineering sensors and various things in as possible. And things just kind of get heavier when you do that. So anyway, we're pretty comfortable with where we're at now. You'll notice this kind of tapered upper shell portion of the rover, and that also houses solar arrays. So the rover is powered by photovoltaic energy from the sun that it collects while it's on the surface. Has a battery inside that it charges up with that energy, and that's used to run all the rover's various different systems. It also allows the rover to survive during the lunar night. And that is something that most missions have not attempted before, so that kind of sets us apart. So that 14 days of darkness that I talked about, where the temperature gets down to sub minus 200 degrees, we're going to try to survive that and wake up the next day and carry on. Formidable challenge, but we think we can do it, so we're going to give it our best shot. The lower chassis of the rover is sealed to house all of the sensitive electronics and prevent that abrasive, dusty lunar regolith from getting inside and fouling everything up. We have a very simple but very robust four-wheel skid steer drivetrain system. So for those of you who don't know what skid steer is, if you imagine the way a tank drives, so a tank has multiple wheels on each side, generally has a track over those wheels, but those wheels only rotate forward or backwards. They don't turn side to side like the front wheels of your car do. That's a skid steer system. So the way you turn is by driving one side either faster or slower than the other side in the same direction or in the opposite direction. So it allows you to do pretty much any radius of turn you want, from driving straight forward or straight back to spinning in place and anything in between, just by controlling the relative speeds of the wheels on the two sides. And our system is driven by a single motor on each side, which drives a pair of wheels. So actually, let's see if I can use my laser pointer here. And I apologize to the people online who probably won't be able to see this, but in this central housing between the two wheels here is a drive motor. And it's a little bit hard to see here, but there's sort of this boomerang-shaped housing that goes from this central pivot out to the two wheels. There's a chain-driven transmission inside of that housing, which transfers the rotation from the central motor to the two wheels. And so that's how we drive. Just two motors, much simpler than the more traditional rovers that you might be familiar with, that you've seen NASA's rovers, which have typically 6 wheels instead of 4, and each of their wheels typically can also pivot. So they have many more motors than we do, way more complex system. And so we're keeping it simple here, and we think we'll do just fine with a much simpler drivetrain system. You'll also notice this little guy is loaded with cameras. So we use cameras both for navigation and kind of just overall situational awareness of what the terrain is like around us, as well as for science. So we have cameras on pretty much all sides of the vehicle and at different heights on the vehicle as well. Some up high, some down very low near the wheels. The top of the rover is a thermal radiator. So this is where we reject excess heat during the daytime. There's a series of there's a thermal system inside the rover consisting of a series of heat pipes and other things that moves heat from inside up to this radiator. And then that radiator is facing deep space, because remember, the sun is low on the horizon. So the sun is shining at us from the side, which is why solar arrays are on the side. And up on top, that sees deep space. So that's a great way to get rid of heat. We also have several antennas, different shapes and sizes that do different things. We have a redundant communications system on this rover. We will be able to talk directly to the lander that takes us to the moon and sets us down on the surface. But that lander is not expected to survive the lunar night. So we will only have that option to talk directly to the lander and have the lander relay our communications to and from the Earth. We'll only have that option on the first lunar day. Then after that, we are truly on our own, and we will have to talk directly to the Earth. So we also have a direct-to-Earth communication system on board. It won't be as fast. It won't have the bandwidth that the system to the lander will, but we still expect to do some meaningful science and engineering operations on the subsequent lunar days. And it's a good backup as well, in case the primary communication system fails for some reason. We have something called single fault tolerance across all the critical systems. And basically what that means is if you have a single failure in any of the systems that are critical to the mission, there's a backup of some type. It might be an exact duplicate system, or it might be a slightly different system that can accomplish the same task in a slightly different way. But basically, there's redundancy there in case of failures. Okay, so I also mentioned there's lots of scientific payload instruments on board, so I'll tell you a little bit about those. The instrument that looks out this kind of rectangular shaped window on the front of the vehicle is a thermal infrared radiometer. This instrument is called LaForge. So for any of the Star Trek fans in the audience, you might recognize that. This instrument is being developed by the Applied Physics Laboratory at Johns Hopkins University in Maryland, in the US. And I mentioned this is a collaborative mission between NASA and the Canadian Space Agency. So the deal is we carry this instrument, this US-based payload instrument on our rover, and in turn, they give us a ride to the moon. So I think we got a pretty good deal, honestly. Not to mention, this is an incredibly capable instrument, so we're really excited to have LaForge on board. What this will allow us to do is determine the temperature of the lunar landscape from the very coldest regions to the very warmest regions that we see when the instrument looks out. So super informative for kind of understanding better just how cold do the cold regions get, including some regions where the sun never actually reaches. So there are regions at the poles in particular called permanently shadowed regions. And these are, for example, the very bottoms of craters. And you can imagine with the sun at a very low angle shining into a crater, you can imagine the very bottom of that crater might not ever see direct sunlight. And that's the primary candidate location for the collection of these water ice deposits. And so understanding those better certainly is of great interest to lunar scientists. And just getting a better idea of the whole environment from a thermal perspective. So this instrument will be very helpful for that. There's a Canadian instrument called the Lunar Hydrogen Advanced Neutron Spectrometer, which is being developed by a company called Bubble Technology Industries in Chalk River, Ontario. This will also work in concert with other instruments that we have on board, including the Forge, with the goal of detecting the presence of water ice. So being able to detect hydrogen signatures is kind of goes hand in hand with detecting presence of water ice. So this instrument will do that. It also has the ability to detect gamma rays. So that's also of interest to sort of characterize the radiation environment on the lunar surface. Very capable instrument as well. Canadensis is providing a number of the camera-based instruments. I mentioned to you, we have a suite of camera products that we've developed. So we're turning those into some science-based cameras as well. One of them will be a multispectral imager capable of taking images in a number of different spectral bands, which allows scientists to detect the presence of various different types of minerals on the surface. There's also a narrow band imager that will see in the approximately 1,000 nanometer wavelength, and this also helps with the detection of water ice. We have, as I mentioned, a bunch of other cameras on board. So in addition to using them for navigation and situational awareness, there is a certain amount of science that can be conducted as well with just a typical color camera. So we have both single and a stereo pair of cameras on the front of the rover, and also other single cameras on the sides of the rover and down low in the front, as I mentioned. So those will also be used for doing context-based science. And one more, there's a microdosimeter, which is an instrument used to measure radiation levels. And again, that's just to characterize the radiation environment at the surface. Okay, so talk a little bit about the approach we take in building a rover. You can imagine a rover being similar to a remote control car. So if you've ever sort of played with a remote control car, you have a pretty good sense of what we're doing here. The main parts of the rover are the structure that holds everything together, motors that make the moving parts move, wheels to make it roll. One interesting point to note here is we can't use rubber tires on the moon due to the vacuum and those temperature extremes that we talked about, and that very harsh lunar regolith. Rubber would not stand a chance. So we use all metal wheels. And I happen to have a prototype of one of the wheels that we have developed for the rover with me tonight. I thought about trying to pass this around, but then I kind of thought maybe it'll be easier if we just let people come up and take a look afterwards. So if you're interested, feel free to come up. It's very light. A couple people had a chance to hold it earlier, and they're super lightweight, but pretty stiff as well. They do have a little bit of flexibility that allows them to sort of traverse over the uneven terrain that we're going to experience on the moon, climb over small rocks, that kind of thing. They're also really good for getting grip in soft sand. So we also expect to encounter lots of that when we get there. So that's the wheels. The cameras I've talked about. This really allows the operator to get a sense for what the surrounding terrain looks like. It's one thing to operate a remote control vehicle when you're standing right behind it and you can see everything around it. It's quite something else to do that without being able to see that. So I've likened this to trying to drive your car with all the windows blacked out and only a small area of your windshield clear that you can look through. So imagine how difficult that would be. Now imagine that the sun is shining directly in your eyes through that little spot in your windshield, and you're driving not on a nice smooth road, but on a rocky, uneven surface. That's what we're up against. And the other challenge is we're not quite close enough that we can drive in real time. So you can't really just drive with a joystick like you might do, or a gamepad controller like you might do if you were just driving a little remote control car that's 10 feet in front of you. There is a small time delay sending a signal to the moon and back. It's about 3 seconds, which doesn't sound like much, but if you actually try to introduce a delay like that in a real-time remote control system, you'll quickly find makes it driving very, very difficult. It's just enough to be problematic. So we really can't drive with a joystick in real time. We have to send sort of short drive commands and drive step by step. And so it slows things down quite a bit, but that's kind of what we're up against. So communications, sending signals to and from the rover or between the rover and the operator. Computers to make everything work together, of course, and then electrical power from those solar arrays and the battery to provide the power. We have to be selective of the materials that we use. So in general, we're selecting lightweight, strong materials, aluminum, titanium. In some cases, we're using carbon fiber as well. And specialized manufacturing methods. Conventional machining is used for a number of parts, but we also do some 3D printing, and that's 3D printing of metal parts. So that's a relatively new sort of manufacturing method that's just kind of finding its way into the space industry, and molds and other things as well. So in terms of the mobility system that moves the rover, this is something that has had quite a lot of development over the last 15 or more years now in Canada. We're up to about the 9th generation of prototypes that we've developed, both at our company as well as other companies in Canada now for rover systems. They are fault tolerant in the way they operate, so that if, as I mentioned, if there's a failure, you're not dead in the water, you can still operate. You also have to find a way to keep that harsh dust out of moving parts. And you really can't use conventional rubber seals for the same reason we can't use rubber tires. So you have to find creative ways to do that. This extreme temperature, from cryogenic cold up to very hot, has to be tested. And also in the vacuum environment, since there's no environment on the moon as well. So we have done some testing in thermal vacuum chambers in the presence of lunar regolith simulant. So simulants that are developed to be similar in their properties to actually to actual lunar dust. And we've done a number of different wheel design prototypes for vehicles, ranging from sort of, the one you see here, right up to wheels that would be kind of the height of this table for much larger rover vehicles, including prototypes of manned crewed vehicles. And we've tested these wheels over thousands of kilometers running over rocks and regolith simulant, and it's been lots of good fun. So night survival, this thermal challenge that I have been talking about is a very formidable challenge. 14 days straight in darkness where the temperature is minus 200 degrees C or colder. So that's, if you're doing the math, that's 354 hours of super cold exposure. So we kind of take a three-pronged approach to this. First, you try to design as many components as possible to just be hardy and survive exposure to those temperatures. Some things you can do that with. There are some that it's very difficult or just cost prohibitive to do that. Things like batteries, for example, and some other sensitive electronic components, very difficult to design them in a way that they would survive exposure to those temperatures. So we have a region inside the rover where we put the most sensitive components, and we thermally isolate that region from the rest of the rover. So we can keep it warm with just a very small amount of battery power over that 354-hour lunar night, and that the heat doesn't leak out of there and escape through the rest of the rover to the environment. And so, you know, we do that with some of the key components. The battery is probably the biggest. Well, the battery is the single heaviest component in the rover for the reason that we still need to rely on it for a little bit of power during lunar night. And we're talking about just a few watts here, like 4 or 5 watts, but 4 or 5 watts over 354 hours is still a fair amount of energy. So you still need a decent sized battery for that. And then we take what we call a graduated approach to surviving lunar night as well. So, and this is an interesting multivariable problem to try and solve. So deciding where you're going to go on the lunar surface is related also to when you're going to go, because you have to go when the sun is going to be shining on that particular location, and you have to know how long is the sun going to be shining. So when I say the lunar daytime is 354 hours followed by the lunar night of 354 hours, not quite true. If the moon were a perfectly smooth sphere, that would be true. But as we know, it's not. So it really is dependent on the region that you land in. And we're talking about variability sort of on the 10-meter scale. So you might find a spot on the moon that on a particular day or for a particular period of time is illuminated by the sun. Because of the surrounding undulating terrain, if you move 10 meters this way, you might be in darkness for that same period. So it's been a very challenging problem to determine where we're going to go. We also need to be able to see the Earth, to be able to communicate with the Earth. So, and the moon has a little bit of an axial tilt, just like the Earth does, not quite as much as the Earth. But for that reason, the Earth also rises and sets above the lunar surface at the pole. And surprise, it's not periodic the same. It's not, doesn't have the same period of rising and setting as the sun does. So sometimes the sun and the Earth are both in view at the same time. Sometimes the sun is in view, but the Earth isn't. And sometimes it's the opposite. So it's a very complicated problem. And so choosing a spot on the moon where we can start out with a shorter lunar night, just because of the combination of all of these factors, is preferable to make sure that the rover is going to work as we expect and we'll survive at least a shorter lunar night. And then once we gain confidence, we can attempt longer lunar nights. But that also involves driving to different locations once we're there. So it's a, as I said, it's a multivariable problem. It's quite interesting. Guidance, navigation, and control of the rover. So we have, as I've mentioned, a number of sensors on board, including cameras that allow us to navigate and see our surroundings. We also have a small LiDAR sensor on the front of the rover, which allows us to take three-dimensional data, so point clouds and build up kind of a three-dimensional terrain map. We can actually see in the darkness a little bit with some lights that we have on board. We do plan to actually do some limited exploration of those permanently shadowed regions that I was talking about. So the vehicle won't be capable of driving into a very large crater, but it could drive into a much smaller crater or partway into a much smaller crater where the terrain is in darkness, take some scientific measurements for an hour or two, and then come back out again, back into the sunlight. The lights that we have on board will help us navigate in those situations. We also have, as I mentioned, a pair of stereo cameras, which allows us to do some additional sort of depth perception navigation capability, gives us that capability. And just measuring the number of times the wheels turn gives us a sense for how far we've traveled as well. It's not perfect because we don't expect the traction of the wheels to be perfect. We do expect there to be some slip, especially if we're driving on a slope, either up or down slope or on a side slope. We do expect to get some slip there. So we can compare that wheel odometry with other indicators of where we've traveled to get a better sense for where we actually are. So how do we build and test this thing? We have several test models that we've been developing over time, and we use them for various different types of tests, including using specialized test equipment to simulate the environments, the various different environments that the rover is going to see during its trip to the moon and once it arrives there. So large pieces of test equipment like vibration shakers. We have large, what we call analog terrains, where we try to mimic the sandy, rocky surface of the moon. It's essentially a large sandbox, basically. We have an indoor facility at Canadensis, and the Canadian Space Agency also has a fairly large outdoor analog terrain, which we use pretty extensively for practicing driving around. We even do tests at night with big spotlights to simulate the moon low on the horizon, casting those long shadows over the terrain and having to drive straight into that really bright light that I was talking about. Learn how to navigate in those conditions, because that's what we're going to be facing when we get there. The one thing that's very hard to simulate is reduced gravity. So we don't really have a good way to do that on Earth. You can do it for very short periods of time. If you take a parabolic flight, for example, there are aircraft that fly parabolic trajectories where at the top of the trajectory, you get a few seconds of reduced gravity or zero gravity, depending on how they fly. Pretty hard to do a rover test on one of those flights. So we don't really do that. And trying to come up with any other way to offload the weight, it's really complicated, and it ultimately doesn't work very well. So we have to try to study this in simulations, computer simulations, things like that, and ultimately just do our best. And we really won't know everything until we get there. So getting the rover to the moon, I mentioned the CLPS program that will be our ride. So the rover will be attached to one of these CLPS lunar landers. That lander will then be mounted inside of a rocket. And after that rocket launches into orbit, it will transit to the moon, enter orbit around the moon, and then eventually descend down to the lunar surface. And with any luck, we will land softly and in the correct orientation that will allow us to then egress the rover from the lander and get our wheels into the dirt and start our mission. We're very much dependent on the lander and the launch vehicle to get us there. We really can't do anything until they do that. So in terms of status of the program, we are currently in what we call the detailed design phase, which is kind of we're about halfway through, really. Canadensis was awarded the prime contract for the phases B, or preliminary design, detailed design, and assembly, integration, and test of the rover. We started that in late 2022. So we're about 2.5 years in, a little more than that now. And as I mentioned, we won't be launching earlier than kind of mid-2028. It'll be in the second half of the year that we launch and land. And that's just, again, due to that seasonality of the sun illumination and Earth visibility at the South Pole. The second half of the year is more favorable than earlier in the year. So yeah, sometime the second half of the year. And if for some reason 2028 doesn't work out, we'll try again in 2029. So landing site selection, I talked a little bit about some of the challenges that go into this. So this has been an area of huge effort over the last 3 years or so. We have a primary landing site selected, but unfortunately, I'm not allowed to announce what it is yet. What I will tell you is it is poleward, or closer to the South Pole, than 85 degrees south. So we're within 5 degrees of the South Pole. This map on the slide here shows the region of the moon that is southward of 80 degrees south. And it's really hard to see, but there is actually a line on the slide here. And again, apologize to our online viewers. There is actually a circle that you can see there that's marked 85 degrees south. So imagine that we are somewhere just inside that circle. And that's about as much as I can tell you right now. This will be announced probably in the coming months as well, because our launch contract with CLPS will be awarded by that time. So NASA will select the CLPS vendor that will win this contract, and will be developing the lander to carry us to the moon sometime this summer. That announcement will be made, and I think at that time they'll also announce what the landing site is. I talked about all these factors. I won't go into too much of those again. We are not the only payload. They call it a payload. The things that are being carried to the moon. We're not the only payload. There are some other international payloads and American payloads co-manifested with us on this mission. So there's enough complexity trying to choose our landing site and landing date without considering anybody else. Well, then we also had to consider other people. But thankfully, they were really good to work with, and we've all agreed on where we want to go and when we want to be there. So now what's underway is actually planning the traverse routes for the rover, assuming landing at a certain place on a certain date. And there are actually, there is some variability in the date as well, because as we know, launch dates get frequently delayed. So we have to consider not just a single date, but a kind of a range of dates. And that changes the traverse a little bit because of the lighting conditions are slightly different, and periods of Earth contact and all that stuff. So something else we've been doing over the last year or so is starting to plug the different components of the rover together, see how they work. We call this a flat sat. just because it's very flat. As you can see, it's laid out on the table here. And this is just sort of a first interconnectivity test of the various systems to verify their compatibility and their functionality. We also have built, as I mentioned, prototypes of the rover itself with these systems inside, and done some testing. This is these are some a photo and video of testing that was done at the Canadian Space Agency's analog terrain. This was last fall, November-ish timeframe, 2024. We're preparing for another one of these test campaigns this spring. First half of June, I think, is where we're currently scheduling this. And each time we go, we'll be testing more and more refined functionality. We learn lots every time we go, and then we go back and roll those lessons into the next iteration of the design and the operations planning. So these are very useful exercises. I mentioned the rover's name hasn't been announced yet. So the four finalist candidates for the name, in case you didn't see this back in December, Pole R, which is kind of a creative way to have the word polar be bilingual, I guess, by not having it be Anglophone or Francophone. Athabasca, which is a river system and glacier in Alberta. The thought was here that if Canada is going to have a series of space exploration missions, why not name them after kind of regions of Canada that have been explored in decades or longer in the past. And since this was the first, the letter A, Athabasca was suggested. So that made the final list. And we also have Courage, or Courage if you're in French, and Glacier or Glacier. So we'll see. As I said, last we heard this name was to be announced this month, but not holding my breath. So we'll find out when we find out, I guess. I just want to acknowledge all of our partners in this work. This is a very large endeavor which requires lots of different organizations, industry, academia from multiple countries and space agencies. We certainly could not do this on our own. So certainly our support from the Canadian Space Agency is very much appreciated. All the other organizations on the bottom of the slide there also are partners of ours in this work. And so we really feel like we have a pretty stellar team working on this. And we're very grateful to be leading the effort here. So with that, I guess that's kind of the end of my talk.
All right, so welcome back. I think this was a huge hit, Perry, so thank you for bringing that along. All right, so we're going to open it up for questions for Perry. Ideally, we'd like for you to come here and maybe ask your question, but if you can't, then one of us will repeat the question for the recording. So who would like to go first? Okay, maybe we'll start at the back. Go ahead. Yeah.
Yeah. Okay. So the question is, why are rover missions between the moon and Mars so different? And one of the differences that you noted was the size. It's not so much the destination that determines the size. Part of what determines the size is the budget for the program. To be completely honest with you, our project budget is much smaller than that of, say, a NASA rover mission. In fact, NASA has been developing a lunar rover as well. It's much larger than ours. It's called Viper. If you may have heard of a NASA mission called Viper. It had a budget that was much larger than ours, and its size was much closer to some of the NASA Mars rovers. Unfortunately, that mission was canceled last year, for a number of reasons. Budget overrun, cost overrun was one of the significant reasons why that mission was canceled. NASA is still working with their commercial partners to try to find a solution to actually fly Viper, because it's almost ready to go. It was in final testing when they decided to cancel the mission. So really, it's sitting there pretty much ready to go. It would need a little bit more budget to finish it and prepare it for launch and actually send it. But yeah, so we're still hoping to see Viper fly, because it would be an incredible mission. There are some other factors, though, that do require different approaches between, say, the moon and Mars. Mars's climate is much closer to that of Earth's in terms of temperature, length of the daytime, so the amount of sunlight and the amount of darkness. The moon is much harder from both of those perspectives. And even the soil on Mars is much less harsh and abrasive than lunar soil is, because of that environment and the fact that wind exists and moves the soil around and takes those sharp edges off the particles. Yeah, so the question is about additive manufacturing or 3D printing, what kinds of materials we're using. We're primarily looking at metals. There are some non-metallic materials that you can fly in space, although there are some challenges with some of those things. So we're focusing primarily on metal additive manufacturing right now. And it's an area of relative infancy in the space industry. Not a lot of 3D printed metallic parts have actually been flown in space. So our mission will be, well, one of the first. I won't say it'll be the first, but it'll be one of the first, and probably one of the first to go to the moon with additively manufactured parts. Yeah, so the question is, how does the rover get deployed from the lander? And the answer is, we don't know yet exactly. So the way this process works is, we have developed a set of requirements for the lander in terms of how it interacts with the rover. So how the rover gets attached, mechanically, electrically, all those things. And then once the lander lands, how does the rover actually get to the surface? NASA does not allow us to prescribe a solution to their CLPS vendors. We have to set out a series of requirements, and then it's up to the vendors to come up with a solution, to propose a solution. So there are a number of ways it could get to the surface. It could drive down a ramp. That's probably not our preferred solution for a number of reasons, but it could also be lowered down to the surface on a platform of some sort that it sits on. We'd probably prefer that one, to be honest. It could be in some kind of enclosure that gets lowered to the surface and then lifted off like a cover on a fancy dinner, you know. That would be pretty dramatic, but yeah, so the answer is we don't know. No, I mean, the rover will be attached to the lander in a fully assembled configuration, and once it's detached, it will be able to just essentially drive away. Right. So no critical failures, no single point failures. But we only have one motor on either side. So how does that work? Yeah. So we can. It's no credible single point failure on a critical system. If you have a component that's critical, like a motor, drive motor, provided that motor is designed in a certain way or can be proven through test to have an extremely low likelihood of failure, then you can get away with having it as a single point, basically. And so that's what we do for systems where it's not practical to carry a redundant spare. Oh, yeah, risk assessment, yeah. So Yeah, it gets pretty extensive trying to assess all the failure modes and the risks, and convince our customer of what types of failures are credible or not credible. And how do you deal with those? How do you mitigate the risk of failure? It's an ongoing discussion, let's just say, with our customer. Yeah. Yeah, there definitely is some lessons learned shared and data. The lunar science community is pretty tight-knit worldwide. Um, certain countries are more forthcoming with their mission data than others. But in general, there is pretty good sharing of data and lessons learned. And even if multiple missions are investigating the same thing, but in two different locations on the surface of the moon, we're going to learn different things. Just the sheer fact of things being observed to be different at two different locations, we learn something just from that the moon is not homogeneous. It's not the same everywhere. It's different, different types of terrain, different types of soil. So yeah, we don't worry too much about, even if we're repeating a similar experiment to something that's already been done, chances are we're doing it at a different landing site, so we're still going to learn something. Right. So yeah, question is, do the solar panels at risk of collecting dust over time? There is some risk there, and all the different modes of regolith, what they call it regolith transport. So the way regolith gets from the ground onto other things, basically. That's not a well understood phenomenon on the moon. We know there are, the ways we know of that it can happen easily is if it gets thrown up by some mechanism like a rapidly spinning wheel or some other thing that lifts regolith off the surface and deposits it on top of something. But then there are some just not really well understood transport modes too. Like there was some evidence from the Apollo missions or earlier lunar surface missions of, at the point when the sun is setting, there's some strange electrostatic interaction that happens that actually levitates the top surface of regolith above the surface a certain distance for a certain period of time, and then kind of right at dusk, and then as the sun sets, it settles down again. It's not conclusive at all. And in fact, one of the recent CLIPS missions that was flown by a company called Firefly Aerospace in the US actually did land successfully and operated for a full lunar day, and was even able to take some photographs as the sun was setting at its landing site to try to see if they could capture any evidence of this phenomenon. So they're still studying those results. Nothing conclusive has come out yet. What we know is, given the relatively slow speeds that we're going to be driving, and I don't think I actually mentioned this in the talk, but in addition to us just driving short segments at a time and then stopping, our top speed, the rover is only designed to be able to travel at a maximum speed of 20 centimeters per second. But we will never, ever drive that fast because people will just be way too afraid of something bad happening. So we will probably be driving more like half of that speed. So 10 centimeters per second. It's really not enough to kick up dust. So if you're thinking of the videos of the lunar terrain vehicle that the Apollo astronauts drove around on the moon, they were driving much faster than that. They were bumping along. There were rooster tails coming off the back. Like, there's no way we're going to have any of that on this vehicle. Way too slow. And the other thing is, because there's no atmosphere to hold dust in the air, there's no air, So it falls ballistically back down to the surface. It follows a ballistic trajectory back down to the surface. So anything that does manage to get to the top of the wheel, it just falls right back down to the ground. So, and the wheels are all below, every part of the wheel is below the lowest part of the solar panel. So there's very little chance of dust actually finding a way from the top of the wheel onto the panels, and certainly no way for it to get high up on the panels. This electrostatic levitation thing, if it exists, it's not believed to be a very strong transport mechanism for regolith. So even if it exists, and even if it somehow manages to transport a little bit of regolith onto the arrays, it won't be very much. No, so all of our science instruments are what they call non-contact sensors. They are able to take measurements at the surface and slightly below the surface without actually disturbing the surface. So without actually digging or drilling or scooping down. There are other missions that do plan to do contact science. So Viper, for example, has a drill. So they were actually planning to drill into the surface and, you know, pick up a core sample basically and analyze it in situ on the rover. But yeah, we are not doing that. Depends on, yeah, if it's, I'm trying to remember. If it's water ice, yeah, I think it will hold, you can maintain water in solid form in a vacuum as long as it's cold enough. So at like sub minus 200, yeah, it can exist as solid. Yeah, can the rover self-right itself if it's finds itself not upright? And the answer is no. No, we are very dependent on a successful landing and a successful egress to the surface from the lander. The vehicle itself is designed to be quite stable. So, you know, if during the course of driving on slopes or what have you, the vehicle, you know, gets tilted by a certain amount, it will be stable. So it will return to, it will remain upright, let's say, up to about 30 degrees in any direction. So, and again, we will never drive on anything anywhere near that. People would be having like a canary, like there's no way they will ever do that. So if we ever see slopes in reality while we're driving of greater than 15 degrees, like that is a very serious situation. Like that's a bad day on the moon if you're having to drive on a 15-degree slope. Yeah. So, but we are very dependent on the lander to deliver us safely.